Welcome to video 2 for conservation of momentum. Okay, so to start this one, let's consider we have two pucks that are sliding towards each other. Now I say pucks because with hockey they're sliding on ice, so it's very, very frictionless. So here's what we have. We have these two pucks. I'll call this one 1, this one 2, and they are sliding towards each other so that they will have a collision. So this one has an initial velocity, I'll call that v1, and this one has an initial velocity, I'll call this v02. Sometime later they will hit, and what we would see is that they are exerting a force on each other. Remember that a force is simply an interaction between two objects. So as these two pucks are interacting, they're exerting a force. Now this also can show a great example of Newton's third law. Notice that these forces, F1, 2 and F2, 1, will be equal in strength in opposite in direction, and they're acting on two separate objects. So these two forces, 1, 2 and 2, 1, are internal forces within this two-puck system. So we got Newton's third law going on. Now, what's probably going to happen is that because of everything that's set up here, they're probably going to bounce off each other after colliding. And they're going to leave with some final velocities, v1 and v2. So notice that until contact was made, there was no interaction between these two pucks. Then during the collision, they exert their forces. I've got those labeled up there. Also notice the nomenclature, 1, 2 versus 2, 1. You know, the force acting on puck 1 because of puck 2. The force acting on puck 2 because of puck 1. And these forces will be equal in strength, opposite in direction, Newton's third law. Now, when they collide, momentum is transferred from one puck to the other. And the changes in momentum for the two pucks will be equal and opposite. So, in other words, the change in momentum for puck 1 will equal the negative change in momentum for puck 2. That's our law of conservation of momentum right there. So let's do a little bit of algebra with this. And all of these are vectors. So doing a little bit of algebra here, and you can work out that algebra if you need to. Notice that what we have then is that all of the final momentum equals all the initial. And that can be kind of a cool way of looking at it as well. Instead of looking at the changes in momentum, sometimes it's a lot easier to look at the initial versus the final momentum of the entire system. So what we can say then is the sum momentum after the collision equals the sum momentum before, momentum being conserved. And this also helps us explain why guns have recoil. So here we have a cannonball cannon system. And the initial momentum for this system equals 0 because everything's at rest. So that means that the final momentum of the system must be 0 as well. And again, you may be wondering, well, how can the final momentum be 0? Well, if we look at it, we would have 0 equals the final momentum of the ball plus the final momentum of the cannon. But these are vectors. We could say that the ball is moving in a positive direction and the cannon is moving in a negative direction. This is why it's important to remember that both the magnitude and the direction have to be conserved when we talk about momentum. So collisions then. We can study collisions in 1 and 2 dimensions. And a collision is simply when one object comes in contact and exerts a force on a second, and usually over a certain time interval. So on a microscopic scale, what causes a collision will be the electrical repulsion between the atoms, because remember, an atom is surrounded by this cloud of negatively charged electrons. So when two objects come in contact, the electrons from one object repel the electrons in the other, and that's really an electrical interaction, the electromagnetic interaction. So you can quite literally say you never touch anybody. When we analyze conservation momentum, or when we use it to analyze collisions, car crashes, billiard ball collisions, baseball bats hitting baseballs, whatever, we can use this conservation momentum, and we can make predictions about final velocities and things like that. So suppose we want to observe a bumper car traveling at a speed v0 towards a second car of equal mass. When the first car hits the second, we want to know what happens. Well, if they're equal mass, and if the first car is moving and the second one is stationary, what should happen is that all of the momentum of the first one will transfer to the second one, so that the first car will stop and the second car will move away at a speed v0. And I have some demonstrations I can show that with an air track in class. Now let's take a look at what happens if we have two objects, or two objects colliding in 2 dimensions. So for example, let's say we have, we're playing pool, so we got some billiard balls. So we got first one, let's say it's moving at a velocity. So that means that it has some initial momentum. And it's getting ready to hit a second one, but notice it's at an offset. So that means that the initial momentum of object 2, let's say it's equal to 0. So what's going to happen is when they collide, they're going to travel at different directions. So so here's our collision. So object 1 is going to go off in this direction with some final momentum. Object 2 is going to go off in that direction with some final momentum. Well, with conservation of momentum, all of the initial momentum has to equal all of the final momentum. But notice if I were to take these vectors and do vector addition, so if I had final momentum 1, and I tried to keep that same length and angle, and put it head to tail with the final momentum of object 2, notice that this should equal the initial momentum, which is just, we have this plus 0, so obviously it's just going to be E0 1. And if I was careful, if I used a ruler and a protractor, and if I carefully drew out the lengths and the angles, this should be what we see. And this should show us that, in fact, momentum is being conserved, because we can see that the initial momentum equals the sum of the final momentum. And when you add vectors, you have to place the vectors to the tail. Moving on with collisions, we can start to talk about how to classify them. Basically, the way we classify a collision is on what happens to the kinetic energy of the colliding objects. So you may have noticed this when you drop a ball, it does not rebound to the same height. That means that the kinetic energy just after colliding with the floor must be less than the kinetic energy before it hit the floor. So let's draw this out. Let's get some pictures here. So here we have a tennis ball falling. Once it hits the floor, it's going to begin to kind of morph a little bit and flatten out. It'll become stationary. And then it's going to kind of pick itself up and bounce off. So if we think about it, what makes this ball rebound is the forces that hold the ball together. They act like little tiny springs. As the ball flattens, as this ball is flattening right here and here, the kinetic energy of the falling object is being turned into elastic energy. And then the elastic turns back into kinetic energy. And depending upon what material the ball is made of, we can then talk about how much or how efficiently that kinetic energy is becoming elastic and how efficiently that elastic becomes kinetic energy once again. So as the ball flattens, energy is being stored in the materials. A watermelon will do the same thing. It'll deform once it hits the floor. However, its deformation is not reversible, as you might imagine. The kinetic energy of the falling watermelon is turned into thermal energy rather than potential. And that can make for a lot of fun. So, when we go to classify collisions, when the total kinetic energy is the same before and after, which means it's conserved, we call that an elastic collision. So an elastic collision, the total sum of all kinetic energy before a collision will equal the sum of all kinetic energy after the collision. So that means if we have two objects that are going to hit, their initial should equal their final. When the final kinetic energy is less than the initial kinetic energy, we call this an inelastic collision. There's always going to be a little bit of friction within materials flexing and deforming, so there's always going to be a portion of that kinetic energy being lost to thermal. So a perfect elastic collision is impossible, but we can get pretty darn close. Finally, when a collision results in the two objects sticking together, the collision is a perfectly inelastic collision. The decrease in kinetic energy in a perfectly inelastic collision is as large as it possibly can be. Now, no matter what kind of collision it is, momentum will always be conserved. So let's make a quick little flow chart to finish things up here. In the elastic collisions, momentum is conserved. So the change in object 1's momentum equals the negative change in object 2's momentum. And the total kinetic energy before equals the total kinetic energy after. And we can think about the objects bouncing off each other with no deforming. The materials do not bend and stretch. During an inelastic collision, momentum is conserved. the materials do deform as they hit, so that means that kinetic energy is not conserved. So the sum of the initial momentum is greater than the sum of the final kinetic energy. And then for perfectly inelastic, momentum is conserved. And once again, the initial kinetic energy is much, much greater than the final kinetic energy, and the objects stick together after they have collided. Well, that's it for video 2.